This is GVSU Team 10 Advanced High Strength Steel Characterization for Roll Forming Senior Project. For Team Intro, this is Carolyn, our team captain, Katie, our point contact, Tyler, our team secretary, Gunnar, and Charlie. For a project overview, our overall project objective can be broken down into three main tasks. The first being researching advanced high-strength steel grades that will work for roll-forming operations, simulating a full production roll-forming line designed to form advanced high-strength steel, and to create a prototype methodology that would replicate the effect of roll-forming without a production model. Specifications were then made for those three main tasks. The material research specifications included choosing material grades that qualify as an advanced high-strength steel, meaning they have a tensile strength of at least 780 megapascals. The material must also be able to be bent to a 2.5 T bend radii. The given profile that the material should be bent to is shown below as a U-channel. At the start of the project, we put a list together of all the proposed advanced high-strength steel grades that could work for the provided U-channel profile. After showing the full list of options to Katayama, we met and decided on the three grades below, two of them being a very similar third-generation multi-phase advanced high-strength steel, and the third being a first-gen martensitic advanced high-strength steel with a little bit higher ultimate tensile strength, but much lower elongation compared to the Gen 3s we chose. Our simulation specifications included determining the amount of overbend needed to produce a 90-degree bend and producing a flower diagram for the three simulations that we were tasked with, one being a prototype and the other two being a production model. The prototype specifications included the parts meeting the provided profile dimensions of the U-channel and having the prototype equipment be transportable back to Kentucky. Some project highlights. Here we have our material portfolio of the three grades we chose and their corresponding properties. All of these materials were tensile, hardness, and spring back tested per ASTM standards. Here we have our COPA results from the prototype 5-pass setup. Once the COPA prototype model was complete, we were then able to work with roll-form solutions and have them machine our 5 designed dies. As you can see in this video, before it enters the 5th and final pass, we have to manually bend it the rest of the way in. Since this is a prototype model, we knew that the angle progression would be a little too steep for this material, but for prototyping purposes, we were trying to keep it as cheap as possible. Once it is manually bent, you can see that it is easily able to go through the 5th pass for the rest of the blank. Nice. Before designing the production dies, we used research and spoke to industry professionals to see what kind of improvements we should do to our die designs from the prototyping results. What we concluded is that we should increase the number of passes to 12 for Gen 3 and 16 for martensite. Since martensite has such a lower elongation than Gen 3, it should have a less steep progression. Should also add roll traps, increase the shaft diameter, add an entry guide pass, add 2 post-forming passes, add flanges to all the dies, increase the drive diameter throughout the line, add relief angles on non-forming portions of the dies, and have them designed to be self-threading. Using the conclusions we formed from the prototyping stages, we were able to form a 12-pass production setup for Gen 3. Pass 0 being the entry guide, Pass 1 being a 15-degree bend, Pass 2, 30 degrees, Pass 3, 45. Pass 4 is a 55-degree bend. Pass 5, 64. Pass 6, 75. And Pass 7, 82.5. Pass 8 gets us to 90 degrees. 9 is 95 for our overbend pass. And then Pass 10 and 11 both being 90 degrees for our finishing passes. After designing the dies, we were able to run the simulation through the Copra FEA software for all 12 passes. The Martensite production dies were similar to the Gen 3, but as I mentioned earlier, with the elongation being lower, we needed 16 passes. So Pass 0 still being the entry pass, Pass 1, 10 degrees, 2, 20, 3, 30, 4, 37.5, and Pass 5 being 45 degrees. Pass 6 was 52.5, 7, 60 degrees, 8, 67.5 degrees, 9, 75 degrees, 10, 80 degrees, and Pass 11 being 85 degrees. Pass 12 was then our 90-degree pass, Pass 13 being the overbend to 95 degrees, and then Pass 14 and 15 being our finishing passes at 90 degrees. Here, we took that 16 pass design and put it into the Copra FEA software. Several theoretical calculations were done to validate our Copra simulations. Higher percent errors in the early stages were due to transitions from linear elasticity to complex plastic deformation. Alignment improved in later stages as deformation stabilized. Simulations are reliable for thinner materials, but for predictions with materials like we are using, such as advanced high-strength steel, may be less accurate. The project's success relied on our detailed research over the capabilities of advanced high-strength steel and roll forming, our completed prototype setup for roll forming with future recommendations and improvements, the complete prototype and production Copra simulations and FEA to verify research and prototype results, and lastly, the collaborative partnership with several companies and industry partners. Our research conclusions include material processing, large variability in material performance among advanced high-strength steel grades, die design and passes. Initial 5-pass setup showed alignment issues, more passes and design tweaks needed. Simulation challenges. Copra is accurate for thinner materials, but have a large amount of errors with materials such as advanced high-strength steel. Testing results. Consistent with supplier data. Springback of 5 degrees noted. Recommendations. Increase passes, optimize die design, address springback, and edge stress. Implications for Katayama include material selection recommendations, die design drawings, testing and validation data, collaborative partnerships with companies like Rollform Solutions and Cleveland Cliffs, and advanced simulation modeling. Huge shout out to our sponsors, Katayama, Cleveland Cliffs, Data M, and Rollform Solutions for making this project possible.